I thought the last video was going to be the last one on this series, but I've been making some improvements and upgrades to the computer and having a great time doing it. But I've also discovered some things that I didn't think were working quite right, and I didn't know why. And I've done some investigation on that, and it's been a real surprise, a couple of the things that I missed. I thought I had everything covered, and then once I started getting into it, I discovered that I had missed a couple of things. I wanted to show you what those were. On previous videos, I said I wasn't going to have a bootloader on disk. I was just going to use boot code in the monitor, but I got tired of flashing the monitor, so I decided that maybe it is easier to have the bootloader on disk instead of in flash. So that's what I did. I moved the boot code out of the monitor and created a separate bootloader and put that on disk. And what it did was drastically simplify the monitor. So what I have to do with the monitor to get CP/M up and running was much simpler. But it also allows me to create new versions of the loader, experiment with different configurations of CP/M, add components to CP/M, and not have to go back to the monitor and reflash it because something's changed, like the number of sectors that the CP/M image requires. So here's what I did. I originally was just reserving sectors 0 and 1, but it turns out that's not really enough space. I needed 512 bytes. So I just said, well, all right, I'll just allocate one physical sector and put the bootloader there. So logical sectors 0 through 3 are where my bootloader are located. Then after that, the CP/M image resides. So that's really the big change. So how this works is the monitor understands how to access a 512-byte physical sector on drive A, the first drive. And what it will do is it will copy the bootloader, which is in sectors 0 through 3. It'll take that off the disk and it'll put it at address 1000 on the computer. And then it'll pass control to this bootloader. And what that bootloader will then do is take the CP/M image off the disk starting at logical sector 4 all the way up to sector 56. And it'll copy that into the top of RAM where CP/M resides. So let's take a look at some of the code changes I made to get the bootloader on disk instead of in flash. The first thing that happened is that the loader that's in flash is very basic. It only required 81 bytes in order to do this. I mean, I've got 32K of flash in this machine, so there's plenty of space, but why write code inefficiently? Just try to keep it as short and as clean as you can. So let's take a look at it. At the top, this is where I'm just setting up the drive controller. I'm putting it in LBA mode. I'm turning on 8-bit transfers, putting those in the feature registers and executing that. That gets the drive controller set up. Then I'm just going to read one sector. I'm putting that in the sector count register. I'm putting zeros in all the LBA registers. That's going to set up for a read to sector 0. And then the last bit down here is I'm setting up for read sector retry, and then I'm outputting that to the ATA command register. That's going to execute this read sector command on sector 0. After that, I'm just waiting for the drive to come out of busy because it's executing that command. And then I'm waiting for data to be ready on the disk buffer. After that, all this does is read as fast as possible and put it into memory. And where it's going to put it into memory is address 1000. I'm going to continuously check this DRQ bit. And when I see the DRQ bit is clear, then I'm done. And I'm going to jump to address 1000. That's going to transfer control to the bootloader I just put into address 1000. This is the bootloader. It's a little more complicated. You've seen this before. This was all code that I wrote for CBIOS for CP/M. This is going to use the deblocking routines I'm going to be pulling things out 128 sectors at a time. I could have done this simpler with 512 byte physical sectors, but I don't know what I'm going to be using this for in the future. I may want to add additional features to it. So I went ahead and just used my CBIOS code to create that, and I'm using the deblocking routines for CP/M, and I'm reading out 128 byte sectors. So again, the same thing, I'm just setting up the drive controller, and then I'm going to start loading CP/M starting at sector 4. I'm going to read it in, and when I'm done, pass control to CP/M. So let's see how that works. Here I am at the monitor, and I'm just going to press the B key, and I'm in CP/M. This message right here was from the bootloader, this code right here, and when that completed loading CP/M, then I get the loading CP/M message. CP/M's taking over. You might remember from the Part 5 video near the end where I was having trouble getting the stat utility to produce the correct free space for each disk on the system. There's a good reason for that. It's because I forgot something critically important for the CP/M file system. Let me show you what that is. In previous videos, I described how CP/M is organized as far as the file system goes, and I described two major components. The disk parameter block contains the dimensions of the file system, total number of blocks in the file system, block size, and a number of other important parameters. BDOS uses the disk parameter block and the directory to find a file. So if you're looking for a specific file or you want to create a file, the directory is a key component. It contains the list of data blocks assigned to a file and the name of the file, its permissions, and a number of other attributes associated with the file. One of the things I forgot when I was writing this CBIOS for my machine is a piece of memory called the allocation map. The allocation map contains a list of all blocks used and unused. It's created by reading the directory. So every time you log in a disk, CP/M will read the entire directory, collect the list of all of the blocks that are present in the directory that are being used, and then will populate the allocation map with those blocks. This is what it looks like. Just a big bitmap. This bitmap is created every time you log a disk. Every time you put a disk in the drive and close the drive and read the disk, the first thing that CP/M does is read through the directory and create this allocation vector. You need one allocation vector per drive. The size of that allocation vector depends on how many blocks you have in your file system. So in this screen, the first block is block 0, and it's marked with a 1, meaning it's been used. So when you see a 0, that means the block is not used. If you see a 1, that means the block is used. So on the very far left-hand side, these are the directory blocks. So those ones that you see on the screen right now, those are all blocks used by the directory. When you were creating your disk parameter block during the adaptation process, you gave CP/M how many blocks to use for the directory. It just marked those blocks as used in this table. So here's some information about the allocation vector memory size. I'm going to start with a 1024 block size. This was the most common block size used for floppy disk systems. And I'll start with an 8-inch single-sided floppy. This was also very common in CP/M systems. 77 tracks, 26 sectors. 2 tracks are reserved for the bootloader and CP/M. 128 bytes per sector, 243 total blocks in the file system. That requires 31 bytes of allocation vector per disk. Now compare that to my hard disk. The virtual drives I use have 256 tracks, 256 sectors, of which 1 track is reserved for the bootloader and the operating system. 512 byte physical sectors, which using the deblocking algorithms gives me 128 bytes per logical sector. but I have 8,160 blocks in the file system. An allocation vector for that block size and those number of blocks requires 1,020 bytes per disk. So if you had 4 drives, A, B, C, and D, you're going to need over 4,000 bytes. That's a lot. So move over to 2048. Take that same drive, an 8-inch single-sided floppy drive. You would only need 16 bytes for your allocation vector per drive. Whereas on the virtual disks on my machine would require 510 bytes per disk. That's still too much. If I'm going to have 4 drives, A, B, C, and D, I'd need 2K of storage for that. That's still too much. I decided to use a 4096 block size. That would give you just 8 bytes on the 8-inch floppy drive. I would need 255 bytes per disk on my machine. And to me, that's more manageable. I would rather do that than move up to the higher block sizes. But you can see the allocation vector gets smaller because of the number of blocks you have in your file system. So what you see on the screen right now is the skeletal BIOS that's provided by Digital Research when you're ready to adapt CP/M to a new machine. The allocation vector is located at the very bottom, and it's right here, these allocation vectors, ALL00, ALL01, 02, and 03. Notice these are 31 bytes. This is what it's set to when you use this file. What you're supposed to do after you've designed your file system is to update these numbers. Well, I forgot to do that. These were the numbers I was using. So the reason that stat was showing bad numbers is I was overwriting these allocation vectors. So my machine would, I would log in drive A, and it would overwrite all of this stuff here. It required 256 bytes, so it would overwrite all of this. And then when I would shift to drive B, it would start here, but overwrite everything below it. So what would happen is that although the directory was fine, and I was able to open files and write to files and read files and things like that, when I ran stat, I kept getting the wrong free space number. And that's because stat looks at this allocation vector table to calculate how much free space is left. And because I had essentially corrupted this table when I switched drives, drive A, drive B, drive C, drive D, I was corrupting this table. Stat was unable to give me a consistent number and an accurate number. And the only reason I got away with that for so long is that I didn't fill up the drive. If I had actually filled up the disk, well, actually, I wouldn't have been able to. I wouldn't have been able to fill up the disk if I was changing drives. I would have gotten a disk full error before the drive was even full. But because there's so much space in these file systems, 8 megabytes, and I didn't have 8 megabytes worth of files, I got away with it, and the only indication there was a problem was this. Well, now that's fixed. Everything can switch to drive B. That drive has been logged in. And now I'm getting the right numbers. And they're consistent. So that problem is solved. I was originally thinking that I would just present all of these virtual hard drives as drive A through drive O, but because of the size of the allocation table, I decided instead to just present 4 drives, A, B, C, and D. But I've got 15 logical drives of 8 megabytes each. So I want to be able to mount those drives on these different drive letters. I have virtual drives 0 through 14, and drive letters A, B, C, and D. So what I did is I created some software to allow me to label volumes and switch volumes in and out. And I call that setvol. So the program is setvol. And setvol just shows you, here's drive A, B, C, and D, but it also shows you what volume number is currently mounted on that drive and what its name is. So I've got another utility called volumes. That shows the list of volumes that's on the machine. There's 0 through 14. They're all 8 megabyte in size. And then I'm giving each of these a name for the software that I've loaded on them. I've also written a utility called label. So I can type label. Let's say I want to use volume 14. So this is going to be volume 14. And I'll just give it test is the name. Now when I type in volumes, I'll see test down here at the bottom. If I want to mount a volume to a drive, I'm going to do set vol. What I do is I just give it a drive letter. And in this case, I'll just do it for drive D. And then the volume number that I want mounted on that drive. Now you can see drive D as volume 14, label test. Every time you run set vol, there's a disk reset. So I'm essentially resetting the drive subsystem so that the drives are all logged in again, so I don't have to worry about corruption in the allocation vector table. So I thought that was a very nice enhancement to constrain the amount of memory that I'm using by just having 4 drives, A, B, C, and D, but still be able to access logical volumes on my compact flash drive. If you've been listening to my description of the CP/M file system and thinking, where have I heard this before? Well, you have heard this before. If you're familiar with DOS, a lot of the concepts that I've been describing inside of CP/M exist in Microsoft/PC DOS. Back in the early 80s, Seattle Computer Products, an employee named Tim Patterson, wrote what would become MS-DOS and apparently used CP/M as the model. So a lot of the early system calls look a lot like CP/M, and the organization of DOS looks a lot like CP/M. Even Gary Kildall said, I've looked at some of the code for DOS, and some of it looks very familiar. It looks just like code I wrote. Rather than file suit against IBM, Gary struck an agreement to have CP/M offered with the IBM PC at the same time that DOS was offered. Which didn't work out very well, but that's the story. If you're familiar with DOS, you'll notice that some of the components are similar to CP/M. There's a command processor module, which in CP/M is the CCP. Then there is a DOS.sys module, which is a lot like BDOS in CP/M. And then there's IO.sys, which is a layer that abstracts some of the hardware from DOS above it. And this would be similar to CBIOS in CP/M. And then on the disk, there's a directory and the equivalent of a disk parameter block that describes the size, the structure of the file system. And then there's an allocation map, which DOS calls the file allocation table. So the concepts in CP/M and in DOS are very, very similar. One of the innovations that I frankly like is that DOS placed the state of the file system on the disk. So everything that the operating system needed to know about the disk is stored on the disk. And that makes it much easier to do simple things like take out a disk and put in a new one, and then just begin using it without having to log it back in, as you do on CP/M. Second thing it did is it made it easy for you to exchange disks. If your neighbor happened to have an IBM machine with a similar disk drive on it, you could just exchange disks and not have to worry about CP/M's many different types of file systems. In fact, let's take a look at what Microsoft even says about DOS. An easy migration from 8-bit 8080Z80 with CP/M to 16-bit machines with 8086. There was claimed compatibility even then with CP/M OS services. So if you wrote an application for CP/M, Microsoft claimed it was very easy to migrate that application to DOS because the underlying system services that the OS provided were the same. No practical limit on file and disk size. Now, that claim at the time was probably true. It didn't take very long before the file allocation table was too small and we needed a bigger one. exact reporting of file size. This is very nice because in CP/M, you can get the file size in sectors, you can get the file size in blocks, but finding out exactly to the byte how big a file is, it's not easy to do. Fast, efficient file structure. I do like this. I do like the fact that DOS had the full state of the file system stored on the disk instead of in memory or in the BIOS as in CP/M. You've got the BIOS owns the disk parameter block, and then it's got this, as you saw earlier in this video, a block of memory set up for, essentially it's an allocation table. It's called an allocation vector. And then you got a directory on the disk. I like the fact that everything is stored on the disk. Now, I know why Gary Kildall did that, just because at the time everything was 8-inch floppies, and the amount of memory that would be required for the allocation vector was very small. You saw that it was like 31 bytes. Access to disks, these 8-inch and 5¼ inch disks, took time. So why waste time accessing the disk every time you need to update the allocation vector when it's just 31 bytes per drive? You could go straight to memory, and it's fast and efficient. It's just that when you get, as you saw earlier, when you get to large disks like mine, these 8 meg virtual hard drives, it doesn't work all that well. I mean, it requires a lot of memory. No need to log in disks. This is also good, although I remember with IBM PCs, there was the issue with the disk change line not being available or not working. And so people accidentally corrupted their disks when the IBM PC did not detect that there was a disk change. No overhead for non-128 byte sectors. That just means that that DOS does its own deblocking, whereas with CP/M it was an option you had to build into your BIOS. File date and time stamping, that was very nice in DOS. A lot of the things that Microsoft was claiming as an advantage against CP/M would go away with CP/M 3.0, but the agreement that Microsoft had with IBM to distribute DOS for $40 essentially put digital research out of business. And that's why I refer to Microsoft as one of the great consolidators. Some people refer to the technology business. I work in technology, and I know a lot of folks who watch these videos do as well. And many times our business is referred to as a cutthroat business. Well, I think it's worse than that. I think it's a polonium poisoning and car bombing business. It's that aggressive. And Microsoft is certainly one of those companies that you either love or you hate. But what they did do was take a fragmented personal computer industry and turn it into the business we have today, which initially was populated by a lot of small and medium business, and then later all of the rest of us that have computers in our home because of the internet. So enough of the divergence, back to CP/M. I wanted to describe BDOS operations so that you could see how they work. To create a file, we simply form an FCB, a file control block. This is what BDOS uses to maintain the state of a file that you're working on. So you create an empty FCB, and then you call the BDOS create function, and that's going to fill this FCB with information. And BDOS is going to create a directory entry for your file and then return. There will be no blocks assigned to your file. Essentially, nothing will have changed other than the directory has been updated with the file information you requested. Here's something I learned about extents. If you watched a previous video where I described the directory entries and what an extent is, I found out how I thought some parts of this worked were wrong, and so I've updated this slide. And here's what I discovered. You can't use every one of these blocks in an extent regardless of the block size in your file system. I thought you could. Well, as it turns out, if you use a block size of 1024, well, then you're going to be using all of these entries. You'll be able to use all of these entries to assign blocks to your file. And that's true until you get up to 4096. And that's the block size I'm using. And what happens is very different. A lot of the things that you'll read about CP/M are assuming a block size of 1024. And I was just taking those conversations and expanding them to block size all the way up to 16384. And it turns out that's not exactly how it works. With a block size of 4096, I can get 2 logical extents per physical extent. If you saw some descriptions about CP/M and they were talking about physical extents and logical extents, you had no idea that what they were talking about. Well, that was me too. I wasn't really sure what the difference was. Well, here's the difference. A physical extent is this directory entry. It's this right here. A logical extent is a grouping of blocks within this directory entry, a physical extent. So I found out that with a block size of 4096, I'm going to have 2 logical extents per physical extent. The first logical extent is these first 4 block assignments, and then the next logical extent are these 4. You're going to see this in a demo in a minute. So what happens as I'm writing sectors to my disk and I'm filling up these blocks, the sectors use count is incrementing. Well, as soon as I get to this 4th block, I get to the end of this 4th block, I get a new extent number. So this might have been extent 0 as I was writing across. Well, when I got to the end of this, suddenly this became a 1. And then the sectors used rolled over to 0. And I started writing again. Well, that's because CP/M is saying, look, these 4 blocks right here are a logical extent. And then these next 4 block entries are a logical extent. So I thought that that would continue. If you went to a block size of 8192, well, that would give you 4 logical extents. No, it doesn't work that way. You only get 2. So if you have a block size of 8192, this will be your first logical extent, and then these 2, this will be your second logical extent, and this is not used. Gets worse when you get to a block size of 16384. This will be your first logical extent. This entry will be your second logical extent, and the rest of this is unused. Now, I understand that this was corrected in CP/M 3.0, that you were allowed then to use all of these block assignment positions as logical extents, but in 2.2, it doesn't. So if you select a block size of 16384, a lot of the space in this extent, this physical extent, is wasted. In a write operation, you're just going to take that same FCB that was populated with your create call. You're going to make a write function call to BDOS. BDOS is going to do a couple of things. It's going to get a bit from the allocation map that's going to tell it which block is free. And then it's going to start writing sectors to that block. And after writing to that block, it's going to update the directory. If you continue writing, if you just keep writing and you fill up that first block that's 009 in this example, CP/M will go back to the allocation map and get another empty block. And it'll start writing to that block and updating the directory. When it runs out of space in block 00A, it'll go back to the allocation map and get another free block, start writing to that block, and then update the directory. So let's take a look at a quick demo to show you how that works. I'm going to demonstrate the CP/M file create function. So I've written a program for that. I called it create.asm. At the top is just equates for BIOS and BDOS. In the beginning, I'm just going to print a message that I'm starting to create the file. And then in register C, I'm going to put the create function call number. And then I'm going to give it the address of an FCB in the D register. And then I'm going to call BDOS. Down at the bottom, this is where the FCB is. I've pre-populated it with the file name that I'm going to create. The rest of this is zeros. It's all going to be filled in by BDOS when I make the call. So I just create my file, and then I close it, after I've created it. I'm doing that with the bclose function number. Put that function number in C, put my FCB in D, and then call BDOS. This is consistent for all of the functions. You're going to put your function number in C. In case of file operations, you're going to need a pointer to the FCB, and then you just make a call to BDOS. The rest of this just prints the status that I'm going to show you on the screen. This is really more for illustration. The real work is done by BDOS, and it's only in these two areas. So let's run it. Let's give it a try. And see, I've got my programs that I'm going to demonstrate. Let's do C:create. There we go. It's created the file. Essentially, this is the directory entry that's been created. User number 0, file name is test, extension is DAT, and then this is the LSB for the extent number. This is the MSB for the extent number, and this is my sectors written. This is reserved. It's always 0. Down below are all of the block numbers that can be assigned to this file. Notice they're all zeros. No data block has been assigned to this file. No records have been written to this file. The only thing that's happened is we've created a directory entry called test.dat. Let's look at that. So this is the directory entry, user number 00. All of these blocks are empty. And my file is there. Let's run the write utility. I'm going to write to that file. So it's opened the file, set the buffer transfer address, and has written one sector to the file. One sector. It's gotten a block assigned, which is block 0008. So let's take a look at that. 0008. Here we go. So I've just put a number of extraneous characters, marching through the alphabet, numbers and symbols. Look at the directory. There we go. There's block 8 and one sector. Now what I'm going to do is run a program that writes block by block. So it's going to fill up a block, then return. I'm going to ask it to write another block, and we'll watch as it updates these extents. Let's take a look. So what it's done is it's written hex 20 sectors, 32 sectors, which has filled up this first block. So block 8 is now full. We're extent 0, and we've got plenty of blocks remaining. Let's write another one. So I have written block 9. 40 sectors have been written. Let's do it again. Here we've got 60, this is in hex, 60 sectors that have been written. We're now on block A. Now watch what's going to happen to these extent numbers. This is extent 0 that we're on right now. So we filled this one up. Notice that sectors has rolled over to 0. It got as far as 128 sectors, decimal 32, 32, 32, 32, that's 128. So it's rolled over from 128 sectors back to 0, and now my extent is a 1. So I'm right here, and my extent has been incremented by 1. So I'm on logical extent number 2 within this physical extent. So now let's write the next block. 20, now block C, block D, block E. Now when I write this next block, watch what happens to this extent up here. So I've filled up the first physical extent with 2 logical extents, starting over. Extent number 2, sector 0, and I've got an empty allocation area. So I'm starting over now with my second physical extent, and I'll write logical extents as I go. So now I'm on the second logical extent in this second physical extent. Now I'm on my third physical extent. Very interesting. This is the write code. It's the same equates as you saw in the open file. And in this case, I'm opening a file. So I load the bopen function number into C and give it an FCB. I point to the FCB and D and then call BDOS. That opens the file. I set a DMA transfer address. This isn't physical DMA like a DMA controller. This is just an address of the buffer you want to transfer data from or to. And then I print a message that I'm writing to the file. I call BDOS with the bwrite function number and point to my FCB. After I'm done writing to that file, I then close the file. Not difficult to understand, actually fairly simple, but I did want to show you the internals of what's going on when you make these function calls. Which now leads me to the last problem I discovered. When I was testing the file system after correcting the allocation vector tables in my BIOS, I then tried to write 8 megabytes, create a single file, write 8 megabytes, fill up the entire disk with that file. I was successful doing that, but I noticed some odd holes in the file. And when I checked the allocation table, there were holes in it, 2 or 3 of them. That was very concerning. I found it and I fixed it. Let me show you what it was. So this was a symptom. When I looked at the allocation vector, there were blocks just randomly scattered in the allocation table that were listed as unused. When I checked this against the directory, there were blocks that were missing. And it was usually the second logical extent. I checked the disk and the data was missing. The position of these holes varied. There wasn't a consistent place where I was getting gaps. So that tells me it's not necessarily a hard timing issue, a repetitive one. It's one that occurs in certain situations. The only place I believe where something like this would happen is in my BIOS, because CP/M has been around a long time and it's been used in a bunch of different machines. If this was a problem inside of BDOS, I'm sure it would have been found before now. So the only thing that's really recently changed is my BIOS. So I started looking at the way I'm using the disk. This is what the manufacturers say that an ATA disk operation needs to look like. So on a read operation, a sector read operation, you're going to set your LBA sector registers to the sector that you want to read. You're going to put the number of sectors you want to read into the sector count register. I always do a 1. And then you're going to put a 20 or a 21H in the command register for a read command. 20 is read without verify. 21 is read with verify. I always use 21. Then you're going to start by reading the status register. You're going to look for the busy bit to clear, because the busy bit will get set. The drive is executing your command. You need to wait until that busy bit clears. After that, read a byte from the data register, read the status register, look for DRQ clear. Is DRQ clear? If not, read the next byte. So this loop continues until you have read all of the data off the disk, after which you're going to exit. So I follow this pattern. Some manufacturers will describe this section with a counter. They'll say sector's 512 bytes, start a counter, read until you count 512 bytes, and then exit. I didn't do that in this driver. I found it easier to use the DRQ bits. Well, the write is supposed to be identical. So look at the sector write. You're setting your LBA registers for the sector that you want to write to. Same thing over here. Set 01 in the sector count. How many sectors do you want to write? I use 1. Put 31 hex in the command register. 30 and 31. 30 is write without verify, 31 is write with verify. I always use write with verify. And then same thing, check the status register, look for the busy bit to clear. After that, write data to the disk, look at the status register for a DRQ clear. When it's clear, you're done. I had a suspicion there was something wrong with this. I was following the manufacturer's description, but I just had a feeling that something was missing. So I took a look at the actual timing on the drive. These are some charts that show the actual timing of bits being set and cleared on a compact flash drive. So I start off with that right here is where I'm giving it the command. I'm writing to the command register a read command. About 400 nanoseconds after doing that, the busy bit gets set. The drive is reading the sector. The DRQ bit gets set about 400 nanoseconds before the busy bit is cleared. And this is me reading as fast as I can from the disk and writing it into memory. After I've read 512 bytes, the DRQ bit goes clear. This takes about 12 milliseconds in total, reasonably fast. So I didn't think anything was wrong with the read portion of my driver. I've never had any issues with the read operation. I think it has something to do with the write operation. So look at what happened down here. I issue my write command. About 400 nanoseconds, the busy bit is set. There's a 700 microsecond setup time where the drive is getting ready for a write operation. Then the DRQ bit gets set about 400 nanoseconds before the busy bit is cleared. This is me writing to the disk. So as fast as I can, I'm writing to the disk. The DRQ bit gets cleared, and this is where I exit my drive write routine. What I did not know, I should have known this, I guess I forgot. What I did not do, because I wasn't expecting it, is that the busy bit gets set again. Because internally, the drive is writing that sector. It takes about a millisecond. After which the busy bit is clear. This takes about 13 milliseconds in total. That's if you're just writing one sector. But if you write sector after sector after sector after sector, like I was doing when I was trying to fill up the disk, you get occasionally this down here. I would put the write command in the command register. My 400 nanoseconds later, busy bit is set. 700 microseconds later, DRQ is set. My busy bit gets cleared. I would write a sector, the usual DRQ clear, and then busy would get set again. Only this time, it could last up to 40 milliseconds. This was short, like 1 millisecond. But down here, I could be waiting for this busy bit to clear for about 40 milliseconds, to which I attribute there were some non-cache writes going on and some wear leveling, some reassignment of internal sectors going on that took a lot of time. And then this busy bit clears. Because I was not accounting for this, I got away with it. This is so short and there's so much overhead in CPM from a cycle standpoint. I never noticed this. I did fine. So when you saw that there was just these little holes, those little holes were caused by this. About every 2 megabytes or so, I get one of these. So here's what's happened. I was returning after this DRQ bit cleared. I was passing control back to CPM. CPM did its thing and came back to write another sector. Well, when this busy bit is set, none of the registers for ATA are valid. You can issue commands all you want, and the drive will do nothing. All the bits are clear. CPM was trying to write another sector, and the driver rapidly passed all of these steps because everything is clear. And then, thinking it had written that sector, went and processed a little more, and came back and did it again. All while the drive is busy. It's not even acknowledging it. So that was causing these gaps in the file system, all because I forgot about this piece right here. So all I did was add another check on the status register. If the drive is busy, hold here. When it's clear, then go ahead and set up your sector registers and so on to write to the disk. This fixed the whole problem. I hope you found this whole video of changes and fixes and upgrades interesting, and I hope to be presenting again in the future. Maybe this project or maybe a different project. But thanks again for spending the time to watch this video.